So, finally, we have seen the transmission structures. Now, I want to spend some time on losses in coaxial lines. We have seen in general that in transmission structures what is the losses. Now, we will calculate losses in coaxial lines, because that has a trick. It's that unless and until one starts doing that, the trick does not come out. That is why we will do that, and then finally we will see various, based on that loss calculations, various coaxial connectors people have made, so that those are used with coaxial lines to connect any device, any equipment for taking the power or measuring power, etc. So, that is important, because a microwave engineer should know thoroughly those coaxial connectors, and that is why we will spend some time on that. This lecture will be on loss calculation and coaxial connectors. So, some sort of theoretical tutorial that let a coaxial line has a lossy dielectric and finite conductivity conductor. That means, it's the conductor or that both the central conductor and the outer conductor, their metal is having a not ideal, it has finite conductivity. Also, let us assume that between them there is a lossy dielectric. That means, not air is not lossy, but some other dielectric. So, how to tackle this problem? Now, the technique to attack this problem is that we assume that these losses, they do not, whenever the materials etc. are not perfect, still the lossless case field distribution and this lossy case field distribution is not much different. Field distribution will not be much different on the medium, because these losses, the devices are not very lossy, then they cannot be used, for power transportation. So, there are losses definitely, but lossless case and lossy case, the field distribution is not much different. On that premise, we first find that for lossless case, assuming lossless, we have found for a coax what is the electric and magnetic fields, that we have already shown in the coaxial line part, that radial field distribution and magnetic fields are circular. So, you see E is equal to A rho and H is equal to A phi. So, that all of we know that it is radially going out electric field and magnetic field is azimuthally circling. So, from that if you remember that the expression for alpha, the attenuation constant is, we need to find out what is the loss and what is the power flow. If we do that, we can find. So, first step is what is the power flow. Power flow will come from, in any transmission structure, the power flow will come from the Poynting vector, and we will have to integrate it over a surface. So, if we do that for coax, we get this. The calculation is shown, I am not spending time on calculation. So, it is V naught square by 2 into characteristic impedance. So, this part is over, that power flow we have done seen. Now, second step is we will have to find the loss, power loss. Now, power loss will be in two ways. One is conductor loss, another is dielectric loss. Now, dielectric loss is easy, as we will see later, but conductor loss, one thing, where is the loss taking place in a conductor? The point is that in a conductor, the current is flowing as a volume current, and you see that is across the propagation direction, and the current, and that means if we do the calculations that is not creating the loss is getting created because the wave is also going diffusing into the conductor, and we know that up to a depth, if it is a perfect conductor, there is no diffusion, the field don't go inside the metal, but in any real metal the fields go inside and they go up to the, actually there is an exponential variation. So, we say that up to one skin depth there are significant field diffusion, below more than that depth there is practically no field. So, that we will have to now tackle, that using Ohm's law we will have to find that volume, that surface current density which is flowing through the volume of the conductor. So, we will have to revoke Ohm's law, then the power loss in conductor PLC, that will be coming from this. The volume conduction current density flows through the conductor volume. Now, this JC, it is flowing in the longitudinal direction, but also it is in the transverse direction, it is going up to skin depth. Beyond that it is insignificant. The heating produced by this volume current is the conductance power loss. So, remember that it goes inside the conductor. If conductor is a bit thick, it will go inside. So, up to one skin depth at least it will go. So, we start from this tangential electric field at the conductor, and from EM theory we know that this tangential electric field will create a conduction current. Now, that conduction while diffusing, it has a exponential variation. This we have seen in EM theory. This is called diffusion equations, etc. So, and that we are saying this is conductivity. There is a transmission coefficient, that means how much it is transmitting inside, because the field when it comes, a portion of that only goes inside, that is called transmission coefficient, and it goes as a propagation constant. This volume current is exponential decaying in the conductor's penetration depth direction, but in conductor loss expression, what we have found, loss expression, the JC needs to be uniform. When we found the lossless case thing, that time JC was uniform, but actually it is not uniform. So, but our expressions are assuming it is uniform. So, here what is the remedy? The remedy is again that equivalent thing, that one can equivalently define an uniform volume current density extending to one skin depth, so that the total current flow remains same. Equivalence means total current flow in both the cases same. In one case it is varying exponentially, another case we are assuming that up to one skin depth it is uniform. So, find out that equivalent current. So, that has been shown here, and let that equivalent current is J subscript EQ, and that EQ will be given by this total by skin depth, because this is uniform. So, now put that. So, once you know GEQ in terms of the total current and skin depth, so you can write this, and putting this you got the PLC, that will be this total current, the tangential current. Now, tangential current, the moment we get, we know that in any real conductor, the tangential current and the magnetic field both are tangential, and their magnitude also same, only their directions in a interface, there are it is a surface. So, they are perpendicular to each other, but their magnitudes are same. Since our previous expression shows that it is magnitude square. So, J t we can always replace with H tan. So, that will do because of this boundary condition for any real conductor. So, instead of J t we will put H tan, and we know the value of H tan in case of coax. So, we will put that, and this is the value. So, conductor loss we can calculate, PLC we can calculate, and this turns out to be this expression. Okay. So, you can find out this. So, as I said that conductor loss, there is a trick. That trick is that it is the diffusion. So, that is an exponential variation, but our lossless case that time we assumed uniform current density. So, the trick is you define an equivalent, that is the only thing. Another thing is once you have the current, tangential current, you can always replace that magnitude wise tangential current in a conductor is equal to the tangential magnetic field. So, we do that, we know the field in coax. So, we have calculated the power loss in this, already we have found P naught. So, we can define alpha c. We will not do that, we will actually PLC we have calculated, we will also find PLD, that means dielectric loss. So, total power loss is sum of that, then divided by the 2 into power flow, that will give us alpha. But from here also I can find alpha c, which is PLC by 2 P naught. Similarly, alpha d will be PLD by 2 P naught. So, let us see. For dielectric it is easy because the fields are, we know between the two conductors in the coax field exists, dielectric also is there. So, their thing is well known formula from Poynting theorem. So, PLD is given by this. So, once you know electric field you can find, and conductivity of the medium you can also earn the epsilon double prime, that is the imaginary part of the dielectric constant, you can find PLD. So, that we have shown to be this value. So, now we sum. So, the total attenuation constant is this by 2 P naught. So, this. So, this is the value. So, if one knows field distribution, actually this we have seen for coax. Now, we have not done for others, but actually in any transmission line structure like rectangular waveguide, circular waveguide, or this microstrip, strip line, or any structure, you can always, this is the basic equation, that power loss or attenuation constant calculation, but knowing the field structure you should be able to find PLC, that what is the power loss. So, you need to understand the mechanism by which power loss takes place, find out this loss. Obviously, Poynting vector will always give you the power flow, from that you can determine. So, you see this attenuation of coax, that is dependent on this parameter. You see others are obviously what material I am, conducting material I am using, that is determining the surface resistance, eta is the thing, that is the constant, omega is the frequency, this is the what dielectric, what is its loss tangent, it is depending that, eta already is there. But another important parameter, at least design wise, is this B by A ratio. You see B A, or actually we can always write this 1 by A plus 1 by B in terms of B by A. So, outer conductor's radius by inner conductor's radius, this is an important parameter for alpha. So, loss or attenuation constant will depend on that. Now, for air field coax, dielectric loss is negligible, because there is in air there is not much dielectric loss. So, conductor attenuation constant, so conductor loss is the main thing. So, alpha c is this. Now, as I was saying, you try for manipulation sake, you define B by A as a xi, and once you do that you can write these, then find out that for which value of xi you are getting the maximum attenuation constant. So, you differentiate and find out. So, if you differentiate this function, you see that this ratio B by A, that is 3.6. This is an important thing. So, that means the conduction loss or conductor loss, that will be minimum if I can choose a B by A ratio to be 3.6. So, this is preferable, then you will choose that, but the flip side of that is B by A also affects the characteristic impedance of the coax. Characteristic impedance of the coax, this is the formula that time we have found when we did the field analysis. V by I ratio is characteristic impedance. So, that if you calculate, this becomes 77 ohm. But generally we have the in electronics industry 50 ohm is a standard, that the devices, the equipments, measuring instruments, sources, we have 50 ohm. So, if a coax is having a 77 ohm characteristic impedance, to minimize loss, that is not acceptable. So, then people thought that okay, so we will have this loss, but we will also make this impedance closer to 50 ohm. Now, also another thing is what happens to with that B by A is equal to 3.6. Okay, loss is minimized, but what happens to the power handling capability? That means how much maximum electric field I can sustain without breaking down. So, electric field inside coax is this. So, obviously, this is maximum when rho will take the value of A, that means because rho extends from A to B, inner conductor to outer conductor. So, when rho will be minimum, E will be maximum. So, breakdown occurs at inner conductor, and that breakdown value is this. So, power handling capacity of coax, you find out for this ED what is the maximum power that gets created there, this. Now, maximize P max with respect to this ratio xi B by A, that turns out to be 1.65, and this if you put in the characteristic impedance is give 30 ohm. So, two considerations, whether you want the loss to be minimum or you want breakdown to take place. Now, one side says that okay, make B by A large 3.6, another side said make B by A small 1.65. The flip side is one side is giving you 77 ohm, another side is giving you 30 ohm. So, the compromised case is that okay, take it 50 ohm, that means do not minimize the loss fully, do not maximize the power handling capability fully, come something in between. If you do not want to use any other dielectric, that means for air field case this is the story. Here one thing I want to say that generally coaxial cables characteristic impedance is 50 ohm, but TV coaxial cables are not 50 ohm, they are 75 ohm. The reason is that when TV antenna, particularly in the TV days, that folded dipole antenna, actually that firstly that antenna itself was having an impedance 300 ohm, folded by folded dipole it can be made to 75 ohm. So, to match that, the TV people they generally prefer a coax cable with 75 ohm thing. Now, you can ask that they could have make it 300 ohm itself, but 300 ohm making is difficult. There is some, because very small values of the very close spacing is required. between the two conductors, because the TV actually initially when TV was in VHF range, they didn't use coax because 2 wires, shielded wires, that was enough to do that. But later when TV got up higher in frequency TV transmission, particularly UHF, they required the coaxial cable. So since the other people, 2-wire people, they are having 375 ohm impedance, so these coaxial people also keep it as 75 ohm. Now, so people now thought that instead of making an air field guide, we will make a dielectric field coax. Obviously that will make a dielectric loss more, so loss will become more, but we will have more flexibility in choosing the diameters. So that is the practice now, that very precision connectors, they use a dielectric filling to design a 50 ohm low loss coax. In this case, we say the dielectric loss will be predominant, that is more than conductor loss. So to handle that, we know from EM theory that in a lossless case epsilon, you replace that epsilon with a complex epsilon. Complex epsilon is not, it is epsilon dash, not plus minus, because this is wave propagation. EM theory books, you see that if we take this as plus, then it would have been not given the losses nature. So that's why it is made a minus, and then this is the thing. So attenuation with this approximation, as we have seen that most of the microstrip dielectric material, they are at least 0.001 to 10 to the power minus 4, 10 to the power minus 5 is the loss tangent. So tan delta is quite less than 1. So alpha d, the dielectric attenuation constant due to dielectric loss, that is something like this. So now people have more flexibility, that they can choose the A by B ratios much more smaller and or larger according to the need. So this is an example of a precision RF cable. You see that this is a RF cables are very precision, they are quite costly also because their loss is quite small. You see this is the central conductor that is protruding from here, and this white thing is a dielectric filling. This actually we have taken out this sleeve. So this is the white is the dielectric filling, and then the inner conductor you can see. Outer you cannot see here because it is already shielded. There is the behind this or beneath this black covering, there is the outer conductor. These are some more views so that you can see it more pronouncedly. This is the central conductor. Now, how we can make a 50 ohm with a dielectric? So let us take Teflon is a very easily available dielectric, solid polyethylene. Its epsilon r is 2.3. So you see that what will be the expression for this? So we are taking it that already we have seen that time that with that B by A ratio 3.6, which minimizes the conduction loss. So with that, but with the dielectric, so it will be 50 ohm. So if we give that Teflon thing, that is also that is also this is Teflon. So that gives you 50 ohm exact characteristic impedance you can easily make. Now you see some coaxial connectors. So already you are familiar with this BNC. In most of the oscilloscopes, megahertz oscilloscopes, you use it. Also in microwave lab, in the VSWR meter you have this BNC, it has a slot. So, when you put it, then there is a, you will have to put that, match that slot, so that it gets fitted there. So, it is a coaxial connector, but this is not a microwave connector, it is generally in the megahertz range people use it. So, these are these connectors have sex, that means one is male, another is female. So, they mate together, and this also I do not know whether you have seen, these are TNC connectors. TNC stands for threaded BNC, they are also have male female sex. Then there are, these are N connectors, these are in many microwave equipments, particularly the network analyzers, you will see these N connectors, they also have sex. Then APC connectors will come just now to their description. APC is a very precision one, but it is quite costly, that is why nowadays people do not use it. Now, SMA was very miniature small ones. So, SMA has various it has various varieties and it is being developed. So, nowadays very high, up to 100 gigahertz you can go with these SMAs, and these are some other varieties of APC, etc. So, previous thing was side view, this is the top view. You see the in new one. Yes. So, actually males as the central conductor comes out, and females you see generally that the central conductor is not there. So, the central conductor of the male that goes into the this female one. Here you can see that this male central conductor that fits inside this groove of the female. Now, this is the N-type connector. You see the, it was named after its inventor P. Nail, that is why N-type from in there. It was in 1942 when the microwave thing were being developed in for radars, for MIT laboratory, etc. That time it was developed. It's obviously you see the outer dia of female is more because it fits there. So, generally all these coaxial connectors, their diameter is specified for female. Outer dia of outer conductor dia of female was 0.625 inch or roughly 15 centimeter. Frequency range up to 18 gigahertz. Typical VSWR, which shows how much how much power is lost in reflection, that means is impedance matching property. So, SWR is 1.07, quite good, 1.07. N-type connector is very much used nowadays, not for very precision, but for moderate precision work N-type connectors are used. SMA connectors, again you see that these are sexes, male and female. Actually, apart from APC, all are male female counterparts. This is name came from sub miniature. SMA stands for sub miniature things, that is why SMA connectors. It was developed a bit later in 1960s, smaller and lighter than N-type. Original outer dia of female was 6.35. So, from 15 of N, so N is more dia. Nowadays, it has got several variations. 3.5 millimeter connector, that means outer dia of female is 3.5 millimeter, 26.5 gigahertz you can go. Then if you reduce further 2.92 millimeter 40 gigahertz, 2.4 50 gigahertz, 1.85 67, 1 millimeter connector we have not I have not seen, but these are 1.85. okay. They are saying theoretically 67, but at least 50-60 gigahertz you can go there. So, you see that a coaxial connector going there, that means told that waveguide will be the higher frequency counterpart of coaxial, but coaxial itself is pushing the boundary and going to millimeter wave things. This is smaller than SMA. Outer dia is this. Excuse me. Then APC, the name comes from amphenol precision connector. This is the only connector which is sexless, only butt contact between outer and inner conductor. So, good, but it is very expensive, not used nowadays. If you buy any very expensive thing, like recently we bought one expensive network analyzer, there it was given APC, but otherwise nowadays most of the things are SMA connectors. BNC connector, as I already said, you have seen this there is a pin here, that pin goes inside this slot and fits there, there is a connection where it is short. This is called baby N connector. N is that after nail, baby N, that is why BNC, not used in microwave region, used in oscilloscope or TV, TNC connector. So, this much we have seen the various transmission structures. Now, this week lecture ends today. In next week, we will try to see that various, apart from this transmission of power, now if I want to divide the power between two or combine the power, how to do that, that type we will discuss in the next week's theme. Okay.